Thank you very much for the introduction. It's a huge pleasure for me to be invited to speak here for the Journée Rham. I'm very sorry that I can't be in Geneva in person. I was quite looking forward to going hiking in Switzerland, first back in April and then in September, but I hope everyone else is doing well in these unusual times, and I hope it is reasonably easy to follow the online version. So in my talk, I'd like to talk about approximating real numbers by fractions. And the basic question that I want to think about is, how well can you approximate a real number by rational numbers? So it's a fairly simple feature that if you're considering any real number, you can approximate it by a rational denominator q up to an error of 1 over q. So if I was, this is just the normal decimal expansion. If I'm thinking about denominators which are powers of 10, I can get within 1/100th of a number by considering approximations, all with denominators 100. And this whole area is known as Diophantine approximation. And the first big theorem in this area is Dirichlet's theorem, that showed that for every real number, so we're thinking of maybe your favorite real number pi or e, there are some special fractions that do rather better. So as I said before, if I'm considering rationals with denominator q, I can always get within 1 over q of any real number, and that's fairly trivial. But Dirichlet showed that there's a sequence of special denominators where instead of getting within 1 over q, I can get within 1 over q squared. And so these are somehow very efficient representations of a number. So one example of this is the very famous approximation of pi as 22 over 7, which is an efficient approximation and is a better approximation to pi than just 3.14. So if you see Dirichlet's theorem for the first time, there's maybe two very natural questions when you understand that every real number has these efficient rational approximations. So maybe the first natural question is, okay, so you can get within, we've improved 1 over q to 1 over q squared. Maybe we could do better than 1 over q squared. Maybe we could find very, very efficient approximations that got you within 1 over q cubed or 1 over q to the 4. And so a natural question is to say, can you improve on Dirichlet's theorem in the same way that Dirichlet improved upon the trivial bounds? And then a second question is that Dirichlet shows that any real number can be sort of encoded by this sequence of efficient approximations. And one might ask, what sort of numbers actually occur in these approximations, and maybe what is the arithmetic structure of these approximations and these denominators? For example, what happens if we only allow denominators from some particular subset of the natural numbers? So let's first consider the first question about better rational approximations. And unfortunately, it's a famous result that there are numbers where you can't do better than Dirichlet's theorem. So in some sense, the worst or hardest approximable number is the golden ratio 1 plus √5 over 2. And for every pair of inches a and q, you know that the distance from the golden ratio to a over q must be at least some constant over q squared. So in fact, you can improve Dirichlet's theorem a tiny bit. You can improve 1 over q squared to a constant which is slightly smaller than 1 divided by q squared. But you can't improve it beyond 1/3 because the golden ratio would be approximable. It doesn't satisfy this. And so this means that Dirichlet's theorem is essentially best possible if you're considering every possible real number, alpha. However, This particular choice of alpha, the golden ratio, is a very special choice, and it turns out that there's a very rich and general theory associated to these so-called badly approximable numbers to do with the Lagrange spectrum and the Markov spectrum. And these sets of sort of counterexamples to improvements of Dirichet's theorem turn out to be a special class of very interesting real numbers called badly approximable numbers. But we think that maybe they're a thin set, and so maybe if you exclude a few bad numbers like the golden ratio and general quadratic irrationals and a few more numbers, maybe you could do your approximations outside of that bad set. However, if you want to just consider every possible individual real number, it's normally exceptionally difficult to really understand how well you can approximate it. So for example, even for some of the most simple and basic real numbers like pi, it's not known precisely how well you can approximate it. So a famous open problem is, are there infinitely many integers a and q such that you can approximate pi specifically with the rational a over q up to an error of 1 over q cubed? We don't believe that this is possible, but no one has shown that it's impossible, and so it might be the case that you could improve Dirichet's theorem for the special number pi. Similarly, you can ask the same number for e or pi plus e, or most of your favorite transcendental numbers, and we really don't have a terribly good understanding. However, if instead of looking for individual real numbers, you look at just most real numbers in maybe a measure theoretic sense, then the question becomes much easier to study. So for example, if you let S be the set of all real numbers such that there are infinitely many approximations a over q that get within 1 over q cubed of your real number alpha, then this set has measure 0 in the real numbers. It's a measure 0 subset of the reals, where measure is Lebesgue measure here. And the proof of this is very simple. You can just consider all real numbers, say between 0 and 1, that has some approximation with denominator q, and it's quite easy to see that the set of numbers is just a union of q different intervals, all of length about 2 over q cubed, and so the total measure is 2 over q squared, and because the sum of 2 over q squared converges, the total numbers which have a approximation of this type with some denominator at least b has measure at most 3 over b, and so this proves automatically that S must have measure 0, because it must be less than 3 over b for every positive constant b. Let's now move over to the other question that I asked, and what if we only allow denominators from some subset? How well can you, say, approximate real numbers with rationals with prime denominators? So this is again a fairly old, well-studied problem that crops up in various different places, and the current world record is a result of Kaiser Mathematici, and so this says for every irrational number alpha, there's infinitely many pairs of integers AP with P a prime, such that alpha can be approximated by A over P with an error of 1 over P to the 4/3. So again, 1 over P is the trivial bound, and Mathematici can get a quantitative improvement over that trivial bound. But it's a very, very difficult result in analytic number theory, drawn upon lots of subtle ideas, and even if you assume the generalized Riemann hypothesis and things like that, we don't know how to improve upon Mathematici's results. So this is a deep theorem to do with prime numbers, but we expect actually the truth should be much, much stronger than this. So we expect that instead of having 4/3, you should be able to have 2, like in Dirichet's theorem, and It's a theorem of Duffin and Schaefer, which is much older than Mathematicus theorem and much easier to prove, that for almost all real numbers alpha, there are infinitely many pairs A and P, such that you get within 1 over P to the power 2 minus epsilon. And so again, almost all here means in a measure theoretic sense. So the set of exceptions, the set of exceptional real numbers between 0 and 1 would have measure 0. And so we've now seen two different examples of a common feature of problems in Diophantine approximation, that if you want to understand questions for every real number individually, this is often impossibly hard, that there are some special real numbers that you can't improve upon things for. There are some special real numbers that behave very strangely compared to others. And for your favorite real numbers like pi and e, we don't really have a very good understanding at all, and you quickly run into famous problems that are over 100 years old, and we don't have any techniques that seem able to get a handle on these things. However, if you allow yourself a measure 0 set of exceptions, then sometimes you can prove much stronger statements. And so this is the fundamental principle of metric Diophantine approximation, that instead of running into all these very subtle and complicated questions that we don't have to answer, if you allow an exceptional set of measure 0 in all your statements, you get a much cleaner and more robust theory where you can often state results that are almost best possible, which is very far away from the normal state of things in Diophantine approximation. And so to combine everything that we've seen so far, I'd like to talk about the main question that I'd like to think about today, where we choose an arbitrary approximation function delta, and we want to try and understand all the real numbers between alpha between 0 and 1, such that there's infinitely many pairs of integers a and q, where you can approximate alpha by a over q up to an error of delta q. And we want to understand this set up to potentially an exceptional set of measure 0. So when we're thinking about approximations of Dirichlet's theorem, that'll be thinking about my function delta being the function 1 over q cubed, or 1 over q to the power 4. When I was thinking about approximations with primes, I'd be thinking about delta being 0 unless q is a prime number, and delta q being maybe 1 over p to the power 4/3, or 1 over p squared when q is a prime number p. So this somehow incorporates everything that we've seen so far. You can choose how big or large delta is on each number q individually, and we'd hopefully like to try and understand this set L for a completely arbitrary function delta. But with this principle of metric Diophantine approximation in mind, we think we're only possibly going to get a sensible answer that we can prove anything about if we allow a measure 0 set of exceptions. So that's the definition of my set L again. And the main result in this area is a very famous theorem, Hintens theorem, proved in the early 20th century. And this says, regardless of what function delta you choose, provided q squared times delta q is a decreasing function, then you can say precisely what this set L is. And in fact, the answer is amazingly nice, that the set L is all of 0, 1, apart from a measure 0 set of exceptions, if the sum of q times delta q diverges. But set L is essentially nothing, so it's just a measure 0 set itself, if the sum of q times delta q converges. So you have this dichotomy, depending on whether you're in the convergence case or the divergence case, where either the set of reals that have infinitely many approximations is essentially nothing, or it's basically everything, and there's this simple criterion to tell which of the two you are. And so this actually gives a almost all extension of Dirichlet's theorem that we were asking, how much better than 1 over q squared can you do? So one immediate consequence of Hintens' theorem is that for almost all alpha, where again almost all means up to a measure zero set of exceptions, there are infinitely many rationals a over q which approximate alpha with an error of not 1 over q squared, but 1 over q squared log q. And this is just because the sum of 1 over q log q diverges. But if we try to improve 1 over q squared log q to 1 over q squared log q to the power 1 plus epsilon, then we know that the sum of 1 over q log q to the power 1 plus epsilon converges. And so that means, by Hintens' theorem, that for almost no alpha in 0, 1, are there infinitely many solutions to alpha minus a over q is less than or equal to 1 over q to the 1 over q squared log q to the power 1 plus epsilon. So this gives a basically sharp threshold for how far you can improve Dirichlet's theorem, and it's just given by this simple convergence divergence criteria. If you wanted to, you could put in lower order terms and consider log q times log q and things like that. So Hintens' theorem is amazingly powerful because it really has very few assumptions on the function delta beyond this condition that q squared delta q is decreasing. And this is the archetypal example of a result in metric number theory, where if you allow a measure zero set of exceptions, you suddenly get this amazingly beautiful and clean theory out of this otherwise very messy and complicated looking picture. So it's precisely the fact that you often have these 0-1 laws where either you have almost everything or you have almost nothing, and there's a simple criterion to tell which case you're in, which is why you get these very nice clean results. And this is why people study metric number theory, that these measure zero set of exceptions allow you to say almost everything is what you want or almost nothing is what you want. However, there's one problem with Hintens' theorem, that it does have this condition that q squared delta q is decreasing. And so, for example, that can't say anything about the case of denominators coming from particular subsets, because as soon as delta q is 0 for some number, that means delta q would have to be 0 for all greater values of q. So a very natural question is, given that we have this beautiful result when q squared delta q is decreasing, what happens if q squared delta q is not decreasing? Can we get some analog of Hintens' theorem then? Maybe some really nice 0-1 law where, again, you say almost everything satisfies these approximations or almost nothing, and there's a simple criterion to tell the difference. Well, it's an old result of Cassel's that regardless of what function delta you're looking at, you do still have a 0-1 law. So even without q squared delta q being decreasing, we do know that this set of reals with these sorts of approximations up to errors delta q either has measure 0 or it has measure 1. So the natural question, given Cassel's result, is, okay, so when does it have measure 0 and when does it have measure 1? In Hintens' theorem, we had a very nice criterion, depending on whether some sequence converged or diverged, to tell us which of the two cases we're in. But it turns out that it's much, much harder to be able to tell whether you're measure 0 or measure 1, rather than just to simply prove that you must be either measure 0 or measure 1. Yeah, so these 0-1 laws always remind me about results from probability. So when in particular, the Borel-Quintelli lemma. So let me just remind you what the Borel-Quintelli lemma from probability theory is. It says if you have an infinite sequence of random events, let's call them E1, E2, E3, and so on, if the sum of the probabilities converges, then almost surely, so with probability 1, only finitely many of the events EJ occur. Whereas if instead the sum of the probabilities diverges, and you also have that the different events are independent from one another, then almost surely infinitely many of these events occur. So this sounds like it's in rather different language. It's talking about probabilities and different events occurring or not. But it turns out it's very closely related to the situation we're thinking about here, because you can just consider the situation that you choose alpha between 0 and 1 uniformly at random, and you can consider the event EQ to be the event that alpha is in is well approximated by a rational denominator q up to an error of size delta q. So it lies in this union of q different intervals. And this then translates our measure theoretic Diophant-Hahn approximation statement into precisely the situation of the Borel-Cantelli lemma. And so the first part of the Borel-Cantelli lemma actually shows that Hintens' theorem extends to all possible functions delta whenever you're in the convergence case. So whenever the sum of q times delta q converges, it's always the case that your set L has measure 0. And this just follows immediately from the Borel-Cantelli lemma and this translation of the Diophant-Hahn approximation setup to a probabilistic setup. Now, if we could show the events EQ were independent from one another, then this would extend Hintens' theorem automatically to a completely arbitrary function delta. But unfortunately, the events EJ are not independent from one another. And so, but you might hope that this is already guiding us along the path of proving an extended version of Hintens' theorem. So that's what I just said. The convergence case already implies that the measure is 0. And so the natural guess would be, even if the Borel-Cantelli lemma doesn't automatically prove this, maybe these events EQ, they're not perfectly independent, but they behave as if they were quasi-independent in some way. And so the natural guess would be that maybe Hintens' theorem would hold for a completely arbitrary function delta. We know that the measure has to be either 0 or 1. And so the natural guess is whenever the sum of q times delta q diverges, the measure would be 1. But unfortunately, this guess is false. So Duffin and Schaefer in the 1940s spent a lot of time thinking about this problem, and they showed that there exists a family of different functions delta such that the sum of q delta q diverges, but nonetheless the measure of the set L of rationals which have infinitely many such approximations is 0. And so this is a bit unfortunate, but if you look at their construction, then morally this is really to do with there being big overlaps between rationals with different denominators that are the same. So it's just the elementary fact that 1 over 2 is the same as 2 over 4 is the same as 3 over 6 allows you to construct special functions where these sets of short intervals overlap with, pile up and overlap on one another a lot. And so there's a very small set of real numbers that have a huge number of good approximations, but then almost all real numbers only have finitely many good approximations. And so they constructed this counterexample, but they realized that because these overlaps are sort of cheating, they're kind of the same rational approximation, a natural thing to do from the technical side of the problem would be restrict to reduced fractions where you can solve any common factor from the range denominator. And so they then considered a set which I'll call lstar, which is exactly the same thing, but instead of looking for pairs of integers a and q, I want to ensure that a and q are co-prime now. So I'm just looking at reduced rational approximations to alpha again, up to an error delta q for an arbitrary function delta. And they conjectured that once you move away from these trivial obstructions due to rationals with different denominators being the same, you should have a perfect analog of Hintens theorem. So for a completely arbitrary function delta, you can choose it exact however you like, from the positive integers to the non-negative reals. The measure of this set L star should be 1 if a certain sum phi of q times delta q diverges, and it should be 0 if this sum converges. Here, phi of q is the number of integers up to q which are co-prime to q, so it's the number of reduced rationals with denominator q. So this is the perfect analog of the Boyle-Cantelli lemma in this setting of reduced rational approximation. So the Duff and Schaefer conjecture has been a big problem in metric number theory for a long time, and there's a huge number of different works that made lots of important partial progress. Duff and Schaefer did very important original work. Then there was later work of Erdos, Wahler, Porrington, Vaughan, Harman, Haynes, Beresnevich, Villani, Eisleitner, and many, many other people who I don't have time to name here. So I apologize if you're sitting in the audience and listening in and I missed your name off. But there's really been a huge amount of work understanding this conjecture. And very recently, just a year ago, my colleague Dimitris Koukalopoulos and I proved that the Duff and Schaefer conjecture is true by building on lots of this previous work. So it is the case that for this set L star, you have a 0-1 law that you either have almost everything or you have almost nothing. And there's a very simple criterion based on a certain series, converging or diverging, which allows you to tell which of the two cases you're in, whether this set is almost nothing or almost everything. So originally we didn't care about the set L star, we cared about the set L. And we know that even if the original version of Hintens theorem doesn't extend, Cassels still showed that Li had 0 or 1, had measure 0 or 1. And so the solution of the Duff and Schaefer problem allows you to have a relatively simple criterion for whether the measure of our original set L is either 0 or 1 based on a convergence-divergence criterion. So this extends Hintens theorem to a completely arbitrary function delta, but you need to have a little bit of arithmetic subtlety in it because you need to consider this function delta tilde, which is just an arithmetic transform of the original function delta, which is the supremum delta tilde of q is the supremum of delta of n over all integers n which are a multiple of q. And up to that subtlety, this modified version allows you to have a simple criterion to tell when you'll measure 0 and when you'll measure 1. There's various other consequences. I don't want to go into these in too much detail, but for example, by plugging in the Duff and Schaefer conjecture to work of Beresnevich and Villani, even when, say, your set L star has measure 0, you can answer some slightly more refined questions, such as what's the Hausdorff measure, and that's based on the critical exponent for, again, a convergence-divergence criterion for a certain infinite sum. So we've been able to prove this result, and this gives us our original result, at least to the original question about can you extend Hintens theorem, and to what extent can you extend Dirichlet's theorem for different sets of different denominators at different strengths of approximation, providing you're allowing yourself this measure 0 set of exceptions, so we avoid these very, very difficult arithmetic questions about how well can you approximate pi. So the proof itself is actually a very fun blend of a number of different ideas coming from classical number theory and analytic number theory and Diophantine approximation, but also bringing in new ideas from combinatorics or ergodic theory, and they all combine in a very satisfying manner. So for the rest of my talk, I'd like to just give a flavor of some of the way that the ideas fit together in the proof, and to give a very broad-based overview, because I think it's very nice the way that we get this very clean statement in Diophantine approximation, but relying on lots of different ideas from different subfields of mathematics. So let's recall the setup based on the Borel-Quintelli sorts of ideas. We're thinking of choosing a real number uniformly at random between 0 and 1, and I'm defining these sets EQ star to be these small intervals around reduced rationals with denominator q, where the length of the interval is essentially my function delta of q. So here I've drawn a picture of what E7 star is, and because I'm only looking at reduced rationals, I don't have a little interval around 0 or 1. And we already know the convergence case that follows automatically from the Borel-Quintelli lemma. So what we want to show is that if this sum phi of q delta q diverges, then almost every real number lies in infinitely many of these different sets EQ star. So the Borel-Quintelli lemma that I stated before requires these sets to behave like independent events. However, if you go through the proof, you don't quite need that they're independent events. It would suffice to show that the intersections of two of these different sets, EQ star and ER star, have measures that look sort of multiplicative. So if the measure of EQ star and intersected ER star was approximately the product of the measure of EQ star and the measure of ER star, and maybe you found some small numbers that went to 0 as Q and R got bigger and bigger, then you could adapt the Borel-Quintelli lemma proof, and that would give a proof of what we wanted. This would show some sort of quasi-independence. But unfortunately, this condition on the measures is far too much to hope for. This is definitely just plain false for arbitrary functions delta. So it's just not the case that the measure of the intersection is the product of the measures for general functions delta. It's maybe quite close to this, but there's certainly going to be fluctuations when sometimes the measure of the intersection is rather smaller and sometimes it's rather larger. However, Gallagher proved an analogous version of Castle's result, and he proved a 0-1 law for this set L star instead of L. So Gallagher proved that the measure of L star is either 0 or its measure 1, and this was based on early ideas in ergodic theory, showing that a certain transformation is a certain measure preserving transformation is ergodic on L star. So this means that as soon as you've shown that the measure of L star is bigger than 1/1,000,000, it can't be 0, so it must be 1. And it turns out that you can adapt the proof of the Borel-Quintelli lemma in a fairly straightforward way. And essentially, this works very nice. This only requires a much weaker notion of quasi-independence for these events EQ star and ER star. If instead of showing that infinitely many of them happen with probability 1, you're just trying to show that infinitely many of them happen with probability at least 1/1,000,000. And so instead of showing that the measure of the intersections is basically the product of the measures, it's sufficient to show that the measure of the intersections is at most 1,000,000 times the product of the measures. And in fact, you only need to show this on average over Q and R. So there's this much weaker condition for quasi-independence where you're allowed to lose some huge constant factor like 1,000,000, and you only need to show it on average. And if you can do this, then that's sufficient to show that the measure of your original set is positive. And a priori, that'd be a much weaker result. But thanks to this 0-1 law, we know that either the measure is 0 or the measure is 1. And so it automatically becomes full measure as soon as we've shown that it's positive. And the key benefit of this is that this sort of upper bound on average is something which might actually be true. So the condition on quasi-independence that we had on the slide before just failed for lots of functions delta, but it's not clear at all that this condition fails for any function delta, such where you're having this divergence criterion. So you can come up with functions delta where this fails, but they have to be, all the examples that I'm aware of have an exceptionally sparse support, and so they would fail the divergence criterion that we're in. So therefore, to make any progress on this problem, a natural thing is to study the measure of these intersections and to see to what extent these, the measure of this intersection of these two sets of rational approximations looks like the product of measures. And so Pollington and Vaughan use sieve methods to get an essentially sharp upper bound to this measure. And I don't want to say exactly what they proved, but roughly they showed exactly what we want, that the measure of the intersection is at most 1,000,000 times the product of the two measures, unless you're in a very specific bad situation. So the only way that things could possibly go wrong is if there's some strong arithmetic conditions linking Q and R. So Q and R both have to have a abnormally large greatest common divisor, and Q and R have to have lots of small prime factors which divide one of them but not the other one. So there are suddenly these quite stringent arithmetic conditions on the denominators, which are the only possible ways that our situation could go wrong. So given this, given the work of Pollington and Vaughan, we want that on average, it's impossible for you to have lots of pairs Q and R which have a large GCD and lots of small prime factors. And if you could show that it's impossible to have lots of these bad Qs and Rs, then maybe there's a couple of bad Qs and Rs where you don't quite have the pointwise bound, but that won't affect our weak Borel-Cantelli attempt, and we can still get an upper bound on average where we just lose a constant factor of 1,000,000 or something like that. So there are two key conditions in the Pollington and Vaughan argument. So let's first think about the second condition, that there's lots of small prime factors. So Pollington and Vaughan actually give you a little bit more information. They have some quantifiable way of measuring what lots of small prime factors means. And so they have some quantification in terms of t, and they give a bound for the measure of the intersection in terms of this quantifier t, which is measuring how many small prime factors Q and R have. But it turns out that very, very few numbers have lots of small prime factors in this way. So using the same measure of quantifying how many small prime factors numbers have, ideas in analytic number theory based on the typical prime factorizations of integers. So if you take a look at an integer at random and you look at its prime factorization, what sort of properties does that have? That's an area of analytic number theory known as the anatomy of integers. And that shows that amongst all integers, it's exceptionally rare that you have this t many small prime factors. And so in particular, the proportion of numbers which have lots of prime factors quantified in this as this function of t is at most e to the minus t squared. And the key point that I'd like to point out here is that the Pollington-Vaughan bound says that your measure is too big by a factor of log t, but this anatomy of integers condition says that typical numbers are rare by a factor of e to the minus t squared. And e to the minus t squared is so small, it completely dominates any losses of a factor of log t, that e to the minus t squared times log t is very, very small. And so this means that if the q's and r's appear in the support of your function delta with anything like a typical frequency, the rarity of such numbers will outweigh any losses you have from having a large intersection measure. And this idea was actually the key part of the work of Erdős and Fowler, who established the Duff-Schaeffer conjecture in some very special cases. However, there's a problematic case that the support of your function delta could be highly concentrated on specific bad numbers with lots of small prime factors, and that could potentially cause problems. But the key principle here is that there are some numbers which can have a bad effect, but typically we expect them to be very, very rare, and so rare we would have thought that this should have no effect on the average behavior of this measure of the intersection. However, to make any further progress, we need to understand the other key condition, which was about these pairs Q and R having a large common divisor. And so a natural question then is, if I have some set of integers where lots of the pairs of the elements have a large common divisor, what must that set look like? And there's one way to construct a large set of numbers where, in fact, all pairs have a large common divisor, and that's just to take all multiples of some fixed large number, because then that fixed large number will be a common divisor from all numbers. And maybe the key part of my work with Demetris on the Duff-Schaeffer conjecture was to show, in some technical sense, this is the only way you can have a large set of numbers where a large number of the pairs have a large GCD. So this is essentially a question in arithmetic combinatorics, and we gave an approximate structure theorem for sets with lots of pairs of elements having a large greatest common divisor. We said either if you have a set of integers where, say, 1% of pairs of elements in your set have a large greatest common divisor, then in some quantifiable way, either your original set must be unusually small, or it must be the case that it essentially looks like this trivial example that I just mentioned, that there's some large number D which divides many elements of your set A. And so this means we actually have a structural theorem that says the only way you can possibly have lots and lots of pairs having large GCDs is if they look very close to this trivial construction. So with this, I guess maybe I should point out that I'm lying slightly and simplifying things quite a lot here to give a key flavor of the new ideas in our work. But it's this approximate structure theorem, which is really conceptually how I like to think of our new contribution. So we're now actually in a stage where we can put everything together to get at least a sketch proof of the Duff-Schaeffer conjecture. So using Gallager's 0-1 law, we know that it's sufficient to just prove whenever we're in the divergence case that we have measure at least 1 over a million, because if we have measure at least 1 over a million, we must in fact have measure 1. Using a weak version of the Boyle-Cantelli lemma, we then see that it suffices to just show that on average, the measure of the intersection of these two sets is bounded above by, say, 1 million times the product of the measures. Using Pollington and Vaughan's bound, we know that this can only fail to be the case if Q and R have some arithmetic properties linking them together. In particular, they must have both a large GCD and they must have lots of small prime factors. But that means that for them, on average, to have lots of for there to be lots of pairs that have a large GCD, we must have some large set of denominators A, such that many pairs of these denominators have a large GCD. But we can then apply our structure theorem to say, actually, A must be surprisingly small, or A must look very close to this trivial construction, where all numbers in A, or almost all numbers in A, just look like multiples of some fixed large number D. So if A itself is very small, then it has a very small effect. And since we only need to get this upper bound on average, it contributes negligibly to the average. And so we can essentially ignore the contribution from these small sets. If we're in the other case, then A has essentially is just the multiples of some fixed divisor D, then you can divide through by D, and you get a situation that's very similar to the work that Arlish and Varla did. And of our set A, we can say that there's very few numbers that have lots of small prime factors in this case, because the numbers that have large GCDs must look just like typical integers from the point of view of the anatomy of integers. So thus, we're done in either case. Our structure theorem gives us two cases. Either we're small and things contribute negligibly, or we're in the structure case, and in that case, numbers look like typical numbers, and so it's very rare for them to have lots of small prime factors based on the anatomy of integers. So I'm almost at the end of my talk, but just to summarize, we used various standard ideas that have been in the subject for quite a long time. So ergodic theory, particularly in the form of Gallagher's 0-1 law, ideas from probability, both to heuristically motivate our manipulations and to use these weak forms of the Borel-Cantelli lemma, which combine exceptionally well with Gallagher's 0-1 law. And then we use some ideas from analytic number theory, in particular this work of Pollington and Vaughan on studying the intersections of these sets EQ and ER using ideas from sieve methods. And this reduces the whole problem to some idea of quasi-independence by showing that there can't be lots of pairs Q and R that have this linked arithmetic bad structure. But by reconsidering the whole problem as a arithmetic combinatorics problem to try and understand the property of pairs of integers having, or pairs of denominators having large greatest common divisors, and by using ideas from the anatomy of integers to understand that for typical numbers, very few integers have many small prime factors, the whole problem is reduced to getting a structure theorem for sets of numbers with large GCDs between many of the pairs, where either they look like typical integers coming from this trivial construction, or the original set must actually be small. And then we prove the structure theorem itself by reformulating it again as a completely separate argument to do with certain weighted dense graphs. And then we use ideas from combinatorics, in particular a compression argument, to prove the structure theorem. And fortunately, putting everything together, we're able to just about show enough quasi-independence that we can make the whole process work. We show we can understand the possible bad exceptions and show that they contribute only a negligible amount to this quasi-independence on average bound. And that's enough to show that the original set had measure at least 1/1,000,000, which then implies that the original set had measure 1. And so we're then able to prove the differentiation conjecture and get a complete classification of these arbitrary approximation functions delta with no restrictions on decreasing or anything. And so it applies for completely arbitrary support. So Thank you very much for listening. I'll pass over to questions now. I hope you enjoyed my talk.